See, as you know, or I mean, this is the message I wanted to give, that algebraic geometry is all about maps, morphisms. You want to study morphism between two varieties. In particular, if you take y equal to point, then it becomes the property of the variety. Okay. So, this is how, I mean, one should always look at that any definition you make, it should be in terms of morphism. So, for example, what is the simplest example of algebraic variety? There are points, finite set of points. So, that means y is the point, means it's spec k. It's a variety over k. This bunch of points. Okay. So this is the, now you want to generalize this for varieties over y. So that means fibers are finite, but you have to be a little bit more careful. So this is a definition. A morphism of f. So let's assume x and y are affine, because that's the simplest case. Then we'll see for projective or quasi or pre-varieties, one can generalize this definition. First, you see that if morphism of affine varieties is finite, if the induced map, so this is, so if giving a map from affine varieties is giving on the K algebra map. So the OY to OX is finite. So finite means what? Finite means this OX is a finitely generated OY module. OX is it's a OY algebra because there is a ring homomorphism. So it's a OX is a finitely generated, is a finitely generated OY module. Of course, it's a finitely generated OY algebra, but this is little bit more, right? Finitely generated OY module is. Or in other words, this is same as saying that you take this f hash of OY. Now, this is a subring of OX, right? This is integral. OX is integral over f hash. Any element here is a is integral over this. It's integral. This is integral extension. Right. Example.
So if it is a finitely generated OY algebra, it would be a finitely generated OY module.
Why? Take K inside Kx. Kx is a finitely generated K algebra. It's not a finitely generated K module. It is very special. Being a finitely generated, if B is a algebra, then B is a module is a very special case. So you will see that these finite maps, when you have a finite map x to y, the function fields are isomorphic. Because function field will be algebraic extension over the one will be contain the other one. So if it is a map from kx to ky, x to y, then kx, the function field will be algebraic extension over ky if this is a finite extension. Okay, so example is suppose you take something injective. Okay, let's say X is affine. We are in affine situation. So take some closed subset here. This is closed. So then you have this map OX. So if it is a closed map, so closed immersion, they corresponds to surject. So this will be a surjective map, right? OX to OY. OY will be some OX mod I. Right, closed subset given by some V of I is zero set of some ideal, where I is right. So any closed subset is some zero set of some ideal, where I is some ideal in OX, and then you consider the corresponding OA. So the corresponding coordinate ring will be OX mod I. Now, of course, this is a surjective map. Any surjective K algebra, they are always finite module, right? If A to B, if this is a surjective, if B is a K algebra, so B is a algebra, B is always a finite module, right? It's clear? But this does not hold for finite A module, yes. You take the one, that one is the generator, right? You take any element B.
Yeah, because it is subjective.
So every element you can write it as f of A. But f of A is nothing but f of A times 1 of B. So that is the 1 is the generator, right? So if it is a surjective map, but you see that if it is a open map instead of closed map, if it is a open map, then this is not the case, because then what, suppose y is d of f, where f is some regular function, right? So then what is a of y? Yes, what is a of y? The regular functions on the open subset df. Df is the basic affine. Huh? No, this is Ox of f, right? Localization at f. But Ox to Oxf, this is an inclusion map. Is it a finite module? If you just take a ring homomorphism A to AF, this need not be finite, right? This is not a finitely generated A module. So you have those generators, they are not finite. So if open immersion, they are not. So this is open immersion, open subset. But closed immersion is a finite map. But open immersion, this is not a finite map, right? So this is a non-example. So what I am saying, that closed injective maps are finite, or morphisms are finite, but open one they are not finite, right? Another example you have seen, the Hilbert, not Hilbert, what is that called? Noether normalization. We have seen the example of a Noether normalization process. You remember how we saw a Noether normalization. So you started with the finitely generated K algebra. So if finite. So let's take A equal to A. Let's take AN. And take some closed subset in AN. So then what is this? This is nothing but K x1, x2, xn. And this is some OX, right? So this is a closed subset. So there is a surjective map. Right. So then what you did in the Noether normalization? So you did some change of coordinates. You wrote there are linearly independent subsets. So transidence degree is okay. I'll write that summation. So you write yj as summation aij xi I equal to 1 to n. Right. And it is it should be automorphism. That means that with the condition that determinant of this matrix aij, this is non-zero. So this is nothing but this is a linear map. So it will give a linear map A into AN. Okay. Now what you said that there exists. So this is AR. I'll just write the diagram, then I'll explain what is going on. So you have this inclusion X going to this map is the composition. This is the isomorphism given by this change of coordinates. Sorry, not this one. This map. This map is the isomorphism given by this change of coordinates. That x1, xi going to this matrix gives you a map of linear map from AN to AN. Since determinant is non-zero, it is an isomorphism. And this is the projection map y1, yn goes to y1, y2, yr. And this r has some special. R is nothing but the dimension of x or transidence degree of the function field of a kx over k. So this is over k. Right. This is just the projection map. This projection map is coming from the this inclusion map. So k y1, y2, yr. So this goes to k of y1, y2, yn. So this map induces the corresponding variety level map, that is AN to AR, and this is the isomorphism, and this is the map which is given by this map, this projection. This is a closed immersion. So now this we saw that this map, this OX is a finitely generated. It's a finitely generated k y1, y2, yr module. Right? That is what Noether normalization says. This is a finite map. You remember, this is Noether normalization. So this map is finite. You could have project to AR, but you have to do little bit of up to automorphism. This projection map, then you do the projection map, then this morphism is a finite map. So this is example, another example. You can canonically construct a finite map. Given a closed subset, you can construct a map to another variety. See, this is always a finite map. Here is a closed immersion, but this is map from X to AN. But this is a map X to AR. This map you are constructing using Noether normalization. So this is an example of another finite. it is a finite module, because OX is a k y1, y2, yr, yeah, it's integral. So this I am saying it's finite module. Okay, so these are some examples. And another some remark. See, if it is a finitely generated, if A to B we have ring homomorphism, B is a finitely generated A module, and if you have a map, if A to B is a ring homomorphism, if this is finite, and if this is finite, then composition is also finite, right? If B is a finite A module and C is a finite B module, then C is a finite A module. So composition of finite is finite.
Integral extension.
Yeah, same thing, yes. So this is one property. Another property is that suppose you have a map from X to Y, and suppose you have suppose F, suppose Z is a closed subset, and you have some W which is a subset of Y. Suppose F takes Z to W, right? Then this, if this map is finite, then F restricted to Z is also finite. So this is suppose these are closed subset. Assume this closed subset. So, yeah, that I will prove that later. But I am saying that suppose you have a finite map, and if you take a subset, closed subset Z, then you will see it's a property of the finite map. The image of closed set is closed. But I am saying a priori, if you just assume that Z is taking to W, where W is a closed subset, then this restriction is also a finite map. Then F restricted. So this is a morphism. So F restricted to F is finite implies okay. So now we want to prove some. So these finite maps are very nice in the sense that what he is saying that it's a closed map. So that means it takes closed set to closed set.
And also fibers are finite.
Fibers are also finite because that is a consequence. But fibers are finite does not imply the map is finite. For example, typical example is this. I mean, there are. I mean, for example, consider this map. Not always you consider the image of maps are closed. I mean, one example of non-closed map. For example, you take this map A2 to A1. This map you just take the projection map. Take the projection map and take the set xy equal to 1. This is a closed subset here. If you take the image is nothing but A1 minus 0, which is not a closed subset in A1. So when you have a morphism, the image of a closed subset need not be closed always. So finite maps are, I mean, but for finite map we will see that it is image of a closed map is a closed set is closed. So it's called closed map. Actually, it is more than that. It's called universally closed. So I will come to that. There are proper maps. Project. But anyway, let's start with basic, very basic, which is okay. So which are finite maps between affine varieties. Okay. So now I recall some commutative algebra result for integral extension or finite maps, which I will use to prove these statements. Okay. Okay, so first I write the variety statement, and then I will recall the commutative algebra results and then prove this. Okay, let me write this. Okay, so proposition. So suppose F is map of affine varieties, finite map, x, y affine. So this is a map of a finite. This is a map of affine varieties. So this will give you at the function at the coordinate ring level. So this you call it f hash. So first property that f is closed. So what does it mean? That means if every close for every if z is closed in X, implies f of z is closed. Second property, right. So so what does it mean? This means a little bit more, right? So this means if it is a finite map from X to Y, yes. So suppose if in particular if suppose f is surjective, image is closed, right? So that's a closed subset in Y. So that's also a subvariety. So in particular, if f is surjective, so that means what? Fz equal to Y. Fz is Y. So what does it mean? What does it say about Oy to Ox? You remember this exercise in Atiyah-McDonald, that if you have a ring homomorphism A to B, this is a surjective, this is injective. If and only if, I think this is if and only if statement, that phi star from spec B to spec A is dominant. Dominant means the closure, that you take the entire image closure is spec A. This is the exercise in the first chapter. I think it was in the first chapter or second chapter. I don't remember exactly. First.
Subjectivity of F will give injectivity of F.
But surjectivity means it is dominant, right? Because it's taking closed subset to closed subset. The closure of the closed subset is the close itself. So that means it's a dominant map at the maximal ideal level also. This is at the prime, but if you take at the maximal ideal level also, it is a dominant map. So that will say that this. So if it is a finite map, so that will say if it is a surjective map, then OY to OX, this map is a injective map. So this is also so in particular, if F is surjective, then F hash is injective. Right. So in the finite map, so this is OX is not just a finitely generated OI module for a finite map. If it is a surjective, see, if when we are thinking finite map, you just think of image, because what is happening outside image, I am not interested, because F is not related to that. So I can always write, if it is a finite, if it is going to a closed subset, then I can always write X to the image of F and forget the other part, because that's not important. After all, I am studying properties of X. So if it is a if it is represented by F, it's a finite map, then this map OX is not a not only a finitely generated OI module, but it is a OI is sitting inside OX as a subring also, right? Okay, so 2. See, now you see that those small exercises in Atiyah McDonald will come into this geometrical thing, geometrical understanding. Those are important. You will see many examples. So next is that.
Sir, our relative spec OYOX.
Huh?
Yeah, high studies map from spec B to spec A.
Yeah, your phi is F hash and phi hash is F. I mean phi hash restricted to spec M, maximal ideal. Phi hash is at the scheme level, at the affine scheme level, but this is you are taking restricting to the maximal ideals.
So that we can correspond to points.
Points of the variety and points of the maximal ideals are Hilbert-Knudsen or algebraically closed field. Okay. So now the second thing is that now suppose you take two subset, closed subsets Z1 and Z2. They are both closed. If properly counted, then you can talk about F of Z1. You know this is closed by 1, and F of Z2, this is closed, but then this also strictly contained in this. If this is a, this is just like property of integral extension. You see, in the integral extension you have this property. If you take two closed subsets, so it will correspond to some prime ideal. Going up, yes. So it is the property of. So now you see the those going up, going down, why did I do in the first few lectures? You will see that this is just application of going up. I always get confused which is going up and which is going down, but anyway, going up or going down.
There was one integral of the.
Yes, so this is the property, or it is a consequence of going up and or going down in for integral extension. So third property is so now it is from the up. Now if I if I start something in down, so it is either going up or going down, something like that. So what is it called? So if you have to assume F is surjective, but F is surjective is not a very serious condition, because if it is not surjective, you could take the image, forget rest, because what will you do with the rest? I mean, there is no way you can relate with F. So always we can always assume the F is surjective. I mean, it's not a bad assumption. If F is surjective, then for any irreducible closed subset W in Y, there exists Z in X such that F of Z, of course Z, I mean Z will be also irreducible, I think. Irreducible. F of Z equal to W. This is third condition, and the fourth condition is that so it is similar like this. So here, but see, this is not only surjective, all closed subset upstairs are going to closed subsets downstairs, and what this is saying, that closed subset downstairs are actually coming from closed subset upstairs. So, but now what about the analogous statement for 2? That means if I have two closed subset, say the W1 and W2, suppose W2 is coming from, so you know that W2 is a closed subset and it is coming from some closed subset of and upstairs. Whether W1, if you take a closed subset W1, that will also come from some W2 prime or W1 prime. But why that W1 prime, whether it will be in the W2, or sorry, what I am saying. What I am saying is, suppose you have two closed subsets, W1 and W2. So you know that this W2 is coming from some Z2. And this W1 will come from Z1, but you don't know whether Z1 is inside Z2 or not, right? What it says that it is actually that is the case. So this is again going up or going down theorem for so if W1, W2, Y irreducible closed subset, and Z2 is sitting inside X as irreducible closed, such that F of Z2 equal to W2, then there exists Z1 closed, Z2 X such that F of Z1 equal to W1. But it is like steps. If you climb steps here downstairs, you will climb similar steps in upstairs. Right. So so these finite maps are like, it's not isomorphism, but it's not very bad. I mean, there is some pattern, or there is some, the map is not very wild. They are very simple maps. After isomorphism, these finite maps are the, I mean, one try to understand these finite maps, right? So this is so we will, so now once you do, I will prove this proposition, okay. Now once you do this for affine case, now you can generalize this for any variety. So what you do, you stay for any variety, first you say that for affine morphism, that means inverse image is for not for any variety, for affine maps. So that means inverse image of affine is affine. And then you say that for affine morphism it is a finite if you restrict to every affine, you have this affine map, f restricted to this affine, if it is finite. That is how you generalize for affine morphism. Okay. And now next, and once you have that, there is something called proper or complete. I don't know whether you have seen in, it's an analog of compact. Inverse image of, yeah, inverse image of compact is compact. That is called proper, right, in topological space. So the generalization of it's generalization. See, in the case in algebraic geometry, everything is compact. So compactness is not a it's not a good condition, because even affine spaces are compact in the usual sense. So but there should be some analog, and that is called what is called projective. So or completeness. We will come to that. We will see that these finite maps are also proper.